Lesson 6 is based on the law of conservation of linear momentum. I am so pleased to share this lesson with you. This is my favorite section of mechanics. To break down this law and fully understand it, let us consider two objects, the block and the ball, which are moving towards each other. This would mean that the block would have a mass m1 and the ball will have the mass m2 because they have different masses. And because I said that they're moving towards each other, it will mean that we'll have the velocity of the block going in that direction and the velocity of the ball going in that direction. And I'm going to label the velocity of the block v1i and label the velocity of the ball v2i. I am putting this label to acknowledge the fact that this is the velocity, the initial velocity of the first object, which is the block. And this is the initial velocity of the second object, which is the ball. Now, this is an initial velocity because if you look at this type of motion, these two objects will eventually get to a point where they collide with each other, as shown in this second diagram. And when they do that, the velocities here must change so that we have new velocities. So we'll have final velocities after they have collided. Hence, we call these ones the initial velocity. This would then mean that this motion that we're looking at will be the before collision. Now, during the collision, which is illustrated by this part of the page, would mean that these two objects will actually be in contact with each other. They'll bump into each other, thereby exerting forces on each other. The ball will exert a force on the block that will be going in that direction. We'll have the force of the ball. I'll call that F21 because it is the force of the second object on the first object. The second object on the first object. Now, because I'm dealing with vectors here, I would love to choose my direction such that I have my direction to be something that sits like this, to say vectors that move to the right are actually positive and vectors that move upwards are also positive. Now, if you look at this vector that I've drawn here for the force, it would be a negative vector because it goes in the negative direction. So here we'll have negative F21. But we know from Newton's third law that the block will also exert a force on the ball. That is the same magnitude but in the opposite direction. So we'll have a force here that is exerted by the block, meaning F12 on the ball. And this vector will be positive because it goes in the positive direction. So we're saying here, using Newton's third law, these two forces would be F12, the force of the first block on the second block, is going to be equal to negative F21, the force of the second object on the first object. These two forces are equal, but they point in opposite directions. Now, when we look at this type of motion, we can see that we have two objects that are interacting with each other. They move towards each other and collide with each other. The interaction is that they exert forces on each other. This type of arrangement is called a system. So a system would be defined to be two or more objects that interact with each other. So if we look at this situation, we have two objects, the block and the ball, and they interact with each other by exerting forces on each other. So the word interact here would mean they exert forces on each other. Therefore, this is called a system. To denote a system, perhaps I can use some dotted lines around these two objects. These dotted lines are called a system boundary. They assist us to see the objects that are within the system. So this object and this object are inside this system, the system boundary. Now, when we look at the inside of our system, we can see that the block has a mass and has a velocity. That would mean that it will also have momentum. So this means that we're going to have a vector for the first object that is given by P1 initial is equals to mass of the first object times the velocity initial of the first object. That is how we defined momentum of an object. It's the product of mass and velocity. In this case, it is the initial momentum because we have the initial velocity and is of the first object. The same is seen actually with the second object, that it will have the momentum P2 initial is equals to M2 V2 initial. That is the momentum of the second object. Now, this means that this system, when we look at it, before collision, it has a total momentum. In other words, if I add this momentum and this momentum, I'm going to get a total momentum of the system. And to do that, we actually use this equation, which is written by the summation of P initial. The summation here means that we are adding is a sum. So we are adding the initial momentum of each object in the system. So this equation really simply says that I'm going to have P1 initial plus P2 initial. And we know that P1 is M1 V1 initial and P2 is M2 V2 initial. That means here I'm going to have P1 initial to be M1 V1 initial, and I'm adding these two M2 V2 initial. This is called the total initial momentum of the system. Is the total initial momentum of the system. So we call this total initial momentum of the system. So basically it is the vector sum of the initial momenta for each object. We are adding the initial momenta of each object. And our system here, we call this system the block ball system because it is made up of the block and the ball. It is made up of two objects, this system. Remember, we said a system has to be a group of objects that are interacting. So a group obviously starts with two objects. If you have more than two, it is still a system. So here our system consists of two things, the block and the ball. So it's a block ball system. Hence, we have the initial total momentum of this block ball system. Now, if we look at the during collision scenario, you would be able to see that these two forces that are exerted by these objects to each other, we call them internal forces. Let me define internal forces before we can get to see how it plays a role in this system. Now, internal forces are forces that objects within the system exert on each other. These are forces that objects within the system exert on each other. Now, if we look at the ball and the ball, they are within the system because they fall within the system boundary, and they exert these two forces on each other. We call those forces internal forces. Now, in a system, internal forces are always equal to 0. If you look at the net internal forces, remember that the net internal force would mean that we are adding all the internal forces. When you use the word net from grade 11, we know that we adding all the forces acting on the objects, or in this case, that are acting on our system. Net internal forces would mean that we are adding all the internal forces together. And I'm saying that the net internal forces in a system will always be 0. Now, to show you this or to prove this, I'm going to come and say I'm looking at the net internal forces. That means I'm going to add F12 to the negative F21. So essentially, I'm just adding these two forces. I'm adding this force and this one. But obviously, this would be a negative here. That's why I have a plus negative. And remember, we said here from Newton's third law, these two forces are equal in magnitude, right? So it means if here I have a 2, I also have a 2 here, but this one would be a negative 2. Right, so that means if I add these two forces, they must actually give me 0 newtons because they exactly have the same magnitude and the other one is negative. So we are going to end up with a negative here. And when you subtract two numbers that are the same, they'll give you a 0. This is to say that the net internal forces will always be 0 in a given system. Now, even though the net internal forces of the whole system is 0, you have to understand that these two objects will exert these forces on each other so that there is an impulse here when they collide or an impact so that these objects will then move in different directions after collision. Let's say, for instance, after this collision, what happens is that the M1, the block, moves in the opposite direction with a velocity V1 final. And the M2 also moves in the opposite direction with a velocity v2 final as a result of that collision. Now, this would automatically mean that this scenario, it is after collision. It represents the after collision effect. Now, because again this object has mass and velocity, they then must have momentum as well. That means here I'm going to have momentum of the first object final, or the final momentum of the first object, which is the block, being equal to m1 v1 final. And the same would be true for the second object. So just to draw this vector, it will be a momentum that goes in that direction. Remember that momentum is directly proportional to the velocity. That's why I draw vectors that are in the same direction there. Here we also going to have a momentum that goes in the direction of the velocity, and that momentum would be given by the final momentum of the second object being equal to m2 v2 final. And again, this would also mean that we can then look at this whole system. Remember, we still have a system here. Everything here, it is still within the system, right? We have a system boundary even in this situation. So that means that we can look at the total momentum of this whole system, meaning we can add this momentum and that momentum to get the total momentum of the system. And running the same mathematics to say the sum of the final momentum of the system would be given by momentum of the first object final plus the final momentum of the second object. And we are saying that the final momentum of the first object will be given by m1, the first object, times the velocity final of the second object. And this would also give me m2 v2 final. This represents the total final momentum of the system, right? It means that it is the vector sum of the final momenta of each object. We're basically adding the momentum of each object. Remember, we do this addition because we are looking at the whole system. We don't consider one object like we did in lesson 1, lesson 2, up to this lesson. We are looking at this as a system, meaning as a group of interacting objects. So when we look at our momentum, we actually add the momenta of each object. When we look at our internal forces, we add the forces that are acting on the whole system, not just one object. However, it is true and important to notice that there is also external forces in this system. But before we talk about the external forces, maybe let's define what the external forces are. So I'm going to define external forces here to say external forces are forces exerted on the system objects by other objects. External to the system. Now, how do I mean here? We're saying that if there's any other objects that are external to the system, that are not part of the system, and those objects exert forces on the objects that are within the system, those forces will be called external forces. To illustrate this, let me quickly redraw our objects that form part of the system. Remember, we have the block. We also have the ball. Now, remember that these two, they form part of the system. they are within the system boundary. They form part of the system. However, it is important for us to notice that they are moving along a horizontal surface here. They are moving along a horizontal surface. Now, there's a couple of interesting things that we have to notice here. The block will experience a force that is exerted by the earth, which we call the force of gravity or the weight. I'm going to write that as W1 because it's the force that is exerted on M1, the block. Now, this force will be classified as an external force because it is exerted by an object that is not part of the system. The earth is not part of the system. Remember, our system is the block ball system. It only includes the block and the ball. So the earth is external to this system. That means the force that is exerted by the earth would be an external force. We also know that this surface here will push the block vertically upwards like that, producing a force that we call the normal force. Again, if you check the surface, it is not part of the system. The surface is outside of the system. So it means this normal force that is exerted on the block by the surface is an external force. Now, this object, when it also moves, if we look at the before collision, the object goes in that direction. It means that the surface will also exert a frictional force that goes in that direction. A kinetic friction force on the block, Fk1. This force again is exerted by the surface, which is external to the system. That means this force will be an external force as well. And the same is true for the ball. We will have the force exerted by gravity, which is going to be F2, which is going to be W2. And the surface will also exert a normal force N2 on the block. And this block, before collision, it actually moves to that direction. That means the surface will exert a frictional force that goes in that direction. This will be Fk2. And remember that our direction is defined in this way. We choose the direction to be in that fashion. We call these forces external forces because they are exerted by objects that are external to the system. To make this to be more fun and interesting, I will further add as well air resistance to say, let's say we have the air blowing in this system. Let's say our wind blows in that direction. It moves such that it moves in that direction. It's going in that direction. This would mean that we will have a force that goes in that direction exerted on the block, and I'm going to call this force FA1 to mean that it is the air resistance or the force applied by the air on the object 1. Object 2 as well will experience this force because it is also experiencing that wind here, as you can see, going in that direction. Now, these two forces, the air resistance, is also an external force because it is exerted by the air. It is not part of the system. It comes outside of the system. It's the air blowing the wind. So it offers some form of air friction or air resistance. Now, it is important to then look at this as a system to say that in this whole system, if I were to find the net external force, the net external force here will be defined by, so we're going to have the net external force. The same logic still applies. If we are looking for the net external force, it means we are adding all the forces acting on the object. So in this case, it means I'm going to have my net external to be given by. Now, you would see that my normal force would be positive because it goes in the positive direction, and my force of gravity would be negative because it goes in the negative direction. Now this means I'm going to have negative W1 plus N2. And we also have air resistance, which goes in that positive direction. So we are going to also add here FA1, and we are going to subtract FK1. This is our frictional force. But we're also going to include in this net external force the forces that are exerted on the second object, because remember, we are not looking at one object, we are doing the net external force for the entire system. So that means here I'm also going to have negative W2, which is this one here, and positive N2. And we still have the force exerted by the air on the second object, and we have the frictional force exerted on the second object. Now, you have to note that these two forces are positive because they go in the positive direction. This equation tells us two things. One, it tells us that the net external force is a non-zero. Right? It can come out to be a non-zero because clearly you can see that if I put values here of all these forces here, I'm going to have a number that is non-zero, maybe 30 Newton or negative 50 Newton. But it is also possible to have a non-zero, to have a zero net force. But that will happen only and if only we ignore air resistance and the frictional force. This means that if we say that there is no air resistance and the frictional force, the net external force will be a zero. Now let's look at how that will happen. If I draw a free body diagram of M1, you have to see that we're going to have the force of gravity and the normal force. Now, we dealt with this extensively in grade 11 where we applied Newton's second law to say this is going to be given by F is equals to ma. And we said that the acceleration will be zero here because if you look at in this direction here, this object doesn't go up, it doesn't even go down. In other words, it has a zero acceleration. It doesn't move in the y direction. But now here we're going to add our forces because the net force is the vector sum of all the forces. That means I'm going to have W1 plus N1. I'm simply taking this force, it's going in the negative direction, and I'm adding that force. And so this means that we are going to have negative W1 plus N1 being equal to 0. And the same can be done with the second object, M2, the ball, where we say it's going to experience W2 and also N2. So that our net force, if we calculate our net force, it will be equals to 0 because there's no acceleration in the y, right? The acceleration is 0 in the y. This object doesn't go down, doesn't go up, right? It doesn't move up and down. So now it doesn't have the acceleration in that direction. So this means that if we compute this normal for this net force here, we're going to have negative N2 plus negative W2 plus N2 being equal to 0. Now, because we are saying here that there is no air resistance and there is no friction, it means these two forces are going to be 0. So if we look at this equation here, we are going to have this part to be 0 and this part to be 0. We are only left with this part and this part. Now, so to rewrite that equation, let me say here I'm going to have net external force being equal to, I'm having W1 plus N1 and I'm having negative W2 plus N2. Remember, I didn't add friction here, and I didn't also add air resistance because they are 0. So these two I've eliminated, I've moved them, they are 0 because we ignore air friction and air resistance. Now we just proved here that this equation here is also 0. So this means here I'm going to have a 0 because this guy here is 0, is equal to 0. And we also said W2N2, this one here, is also a 0. That means here I'm going to have a plus 0 because both this and this are 0. And this would mean that my net external force will be 0 Newton. Now this force here would be 0 Newton. But this happens only and if only there is no air resistance and there is no frictional force. Now, this means that our system, if we look at our system under these conditions, remember this is our system. These two objects are in the same system, right? They are in the same system here. If we say there's no air resistance and there's no frictional force, we find that our net external force is equal to 0. This type of a system where the net external force is equal to 0 is called a closed system. Some people call it an isolated system. Just to give you these definitions, I will write it down to say a closed system or an isolated system is a system in which the net external force is 0, right? Exactly what we proved here at the top to say if our net external force comes out to be a 0, then we call that system a closed or an isolated system. With all this information that we have broken down, we are now ready to then define the law of conservation of momentum, which actually says that the total linear momentum of a system, of an isolated system or a closed system, is conserved or is a constant. So what are we saying here? We're saying that the total linear momentum of an isolated system remains a constant. That means if we take the total linear momentum before collision, which is here the sum of Pi before collision, it must be the same as the sum of Pf, the final total momentum, because you're saying it's a constant. To say things are a constant means that they are exactly the same. Now, if we look at our diagrams here, just to make sense out of it, is that if we look at the before collision, this total momentum that we found here, if it happens to be 2 kilogram meters per second, these objects will collide and then move in the opposite direction, giving us the after collision. Now, we're saying also this number here would be 2 kilogram meters per second is a constant. It gives you the same number of 2 kilogram meters per second. That is what we mean when you say it is constant or it is conserved. It doesn't change. But obviously we can expand these equations to say that when we have the summation, the symbol of the summation, it means we are adding the momentum, the momenta of each object. So for the first object, we're going to have m1 v1 initial plus m2 v2 initial. And this law doesn't only apply to two objects as we have done in this scenario that I was looking. We can have more than two objects because remember it's a system, it's a collection of objects that are interacting with each other. So we can still have plus other objects here. Now this momentum that we have initially should be equals to m1 v1 final plus m2 v2 final, and there could be other objects there that are included. So you can have more than two objects. In the CAPS syllabus, you're only restricted to solve 3 objects. They could give you a maximum of 3 objects to solve. The last part that I would love to share with you on this topic is different conditions that can arise in this law. So there's 2 special cases that you will get when we use this law. The first case would be that when the masses are in proportion with each other. So we're going to look at the case where masses of the objects are in proportion with each other. When I say masses are in proportion with each other, what I mean by that is that the masses are such that, let's say we have the first object here to have a mass of m1 is equals to m. And let's say we have another object here that has a mass of m2, but the mass of m2 is saying it's twice m, is twice as big. So these things are in proportion because the ratio here is, 2:1. This is twice that one, right? So it is 2:1. We call this masses that are in proportion. Let's say that this objects are moving towards each other with initial velocity of 1 to be v and initial velocity of 2 to be v2I. Now these objects will collide with each other here so that they exert forces on each other, and then we'll have the after collision where these objects will then move in opposite directions. Let's say we assume that they move in opposite directions. Now, let's say they move such that our final velocity for 2 is that, and our final velocity for, so this is not 2 here, it is 1. So this will be the final velocity of 2. When we apply our law, and of course here we assume that the system is isolated, meaning there are no net external forces acting in the system. And you have to realize that this is before collision, this is during collision, and this is after collision. If it's an isolated system, our momentum, which is m1 v1 initial plus m2 v2 initial, our total momentum before the collision would be equal to our total momentum after collision. So I'm having m1 v1 final plus m2 v2 final here. But now we're going to substitute our mass here to say the m1 we said is an m, and we still have v1 initial, and here we're going to have a 2m because we said it is twice as large, right? We said it is twice as large compared to the first one. And here we're going to have v2 initial. Now here I'm going to have m v1 final. I'm going to have 2m v2 final. You have to realize that I can divide each term here by the m because I can see that this m is a common factor. In other words, I can divide here by m, divide here by m, divide here by m, and also there by m. Now you would see that the m and the m would cancel each other, so that I'm only left with v1 initial plus 2 v2 initial is equals to v1 final plus 2 v2 final. Now when you look at this formula, it has changed such that we don't have m anymore. This means that if I were to calculate any of these velocities here, I don't need the mass. For example, if I have this and this and that, I can just calculate this. I'll take this to this side and find the value of this. So it means this velocity here, it is independent of the mass. And the same is true even if I do this one. If I were to calculate this, I will just put the values of these other ones and get this one. So the value there wouldn't depend on the mass. The mass wouldn't be part of the equation. So we are learning here that if the masses are in proportion, therefore it means the velocities of the object are independent of the masses. We don't need the masses to calculate the velocities. This happens when the masses are in proportion. If you have, here m, 2m, or maybe you have here 1 over 2m and here you have 3m. Maybe you have 4m and this side maybe you have 2 over 3m. Those masses are in proportion. They will cancel out in the equation. This is a special case that you have to be able to see when you solve problems. The other special case that we have with the law of conservation of momentum is a case that involves objects that combine or separate. So you have objects that combine, or maybe they separate before or after collision. So let's say we have here a block of M1 and is moving in that direction with V1 initial. Then there is another block here, M2, and is moving in that direction with V2 initial. The two, they collide during collision, so that when they collide here, they stick together. So they deform, they change shape and combine with each other and stick together. Now, after collision, these objects then move as one unit. They move as one object because now they have combined. Now, you have to realize a couple of things when this happens. Let's say they move such that maybe they go in this direction. You have to see that the velocity of the first object final, the velocity of this object as it moves in that direction, will be the same as the velocity of the second object. The second object here, V2 final, because they are now moving as one thing. So they move with the same velocity. So the velocity of this and the velocity of that is the same. They move with the same velocity. Because these two velocities are the same, when this is 2 meters per second, also this is 2 meters per second, we can write them as one symbol to say they are given by V final, right? So it means they're moving as one unit with a velocity of V final. The other thing that we have to notice is that this object would have mass M1 plus mass M2. That means I'm adding the mass of this first object with the mass of the second object, and I can say this mass is the same as one big mass. We get one big mass because they move as one thing. Now, when we apply our equation, we will have M1 V1 initial plus M2 V2 initial. This is the total momentum before collision. It will be equal to M1 V1 final plus M2 V2 final. But this total momentum before collision will only be equal to this total momentum after collision if and only if this is a closed system, meaning there are no net external forces. So we're going to assume that in this collision here, there are no net external forces. Now, if we rework this equation and substitute the information that we now have, you'll find that we will still keep the initial total momentum the way it is. But this side here, I'm going to have M1 and I'm going to have V final here. I'm rewriting this V1 as V final because they are the same, right? All these three velocities are the same here. They have the same magnitude. And here I'm going to have M2. I'm going to write V2 final as just V final because again, these two are the same. Remember, they move as one unit. You have to notice that if we continue with this problem, we will have our initial total momentum to be the same as it is. But this side here, I have a common factor of V final, meaning I can take that V final out of the bracket so that I have M1 plus M2 multiplied by V final. Remember, if I multiply this and that, I'll go back here. And if I multiply this and this, I'll go back there. So I'm just taking it out as a common factor. However, M1 plus M2 is actually now equal to this big M. That means here I'm going to continue having this as it is. And here I'm going to have big M times V final. If you look at what this means here, it's saying that this object here after collision, it actually has a final momentum of M V final, you know, the big M here, V final, because we're saying this velocity times the mass, right? Mass times velocity is going to be our final momentum here, because they then now move as if it's one object. They don't move as separate objects. This is very important to know for problem solving, and we'll practice this a lot in the next videos where we do questions.